Hello friends, today we are going to look at how to calculate lattice energy of sodium chloride using the BORN-HABER cycle. Recall that the BORN-HABER cycle from the last lecture is an expression of the Hess law applied to an ionic compound. And according to Hess law, we know that the enthalpy change of a reaction should equal the summation of the different enthalpy changes involved in the different reaction steps or individual steps of that particular reaction. And we understood that when we are treating the energies associated with the formation of ionic compound, we have to pay attention to observing the enthalpy changes for each of these steps. And that summing up the enthalpy changes for all of those steps, the value we made should equal the value gotten had it been we measured the enthalpy change for that reaction in one step using a calorimeter. The calorimeter now helps us to measure the standard heat of formation if the constituent elements actually reacted in their standard state in one-step process to give us the sodium chloride. However, that's not the full story. The BORN-HABER cycle helps us to break down the reaction into the key reaction steps, in which case, talking about sodium chloride, according to BORN-HABER cycle, there are 5 key reaction steps involved in the formation of sodium chloride, and all of these reaction steps each has some energy associated with it, or energy content, or what we call the enthalpy changes. So we have to know what these enthalpy changes for all of the reaction steps are. We have to know how to sum them up, and we have to ultimately know how to use them to find the missing link, which is the lattice energy in that reaction or in the formation of that ionic compound. So let's dive straight into it. So if elements like sodium in the standard solid state react with half mole of chlorine gas in the standard gaseous phase, if they react directly, they will ultimately want to give us sodium chloride, which is a solid. And every reaction has certain amount of energy involved in that process, either absorbed or released. So if sodium in the solid state, which is the authentic natural state, react with half mole of chlorine, which is in gaseous phase, which is the standard state, it's going to give us sodium chloride. That is the overall reaction, but doesn't tell us the full story. So using what we call the calorimeter, we can measure directly the energy that is associated when this element, the constituent element, react in their standard state in one-step process. And using the calorimeter, we can find what we call the overall enthalpy change, or the enthalpy change of the reaction, or what we call the standard heat of formation. In this case, is measured to be minus 411 kilojoule per mole. However, according to BORN-HABER cycle, this reaction actually proceeded in 5 key steps. And each of those steps has some energy content or enthalpy change involved. So instead of going downwards now, we are going upwards in the anti-clockwise direction till we get to sodium chloride. That is what the BORN-HABER cycle is telling us. All right, so if we go upwards in the first step, what happens is that the first reactant becomes the target, where the first reactant, sodium in the solid phase, is changed to sodium metal in the gaseous phase. That's the first thing that happens, okay? And if you are changing something from solid to gas, you are doing sublimation. So the enthalpy change here is called enthalpy of sublimation and is measured to be plus 109 kilojoule per mole. Because this is a positive value, you will agree with me that energy was absorbed in this reaction step. If it were to be minus, that means that energy was released in the reaction step. Beautiful. So move over to the second step. In the second step, the target here now becomes the second reactant, in which case we have half mole of chlorine, okay? Half mole of diatomic chlorine. This is a gas. So the idea here is that how do we free up one chlorine atom, since that is what is just one atom of chlorine that is required to combine with sodium to give us 1 mole of sodium chloride, since we are talking about lattice energy. And if that happens, our interest is how do we break the covalent bond that is holding 2 atoms of chlorine here, okay, to give us half mole of chlorine, which is 1 atom of chlorine in the gaseous phase. So what happens is that the covalent bond holding chlorine to chlorine here is broken in this particular step. So the energy required to dissociate the bond or to break that covalent bond is called the enthalpy change is called the bond dissociation energy, delta H BDE, bond dissociation enthalpy or energy, which is also known as what? Enthalpy of atomization, because you are changing chlorine from the molecular state form to a free gaseous atom. You are atomizing it. You are breaking the covalent bond holding the two atoms of chlorine so that you can be able to liberate atoms of chlorine, in which case one atom can be able to now react with what? One atom of sodium to make the ionic compound. So instead of calling it enthalpy or of dissociation, you can call it bond dissociation enthalpy, or again, you can call it enthalpy of atomization or atomization enthalpy. Again, you can call it what? Enthalpy of dissociation or bond dissociation enthalpy, or you call it enthalpy of what? Atomization. That's what happens in the second step. And this enthalpy of atomization or bond dissociation energy is measured to be plus 120 kilojoule per mole, which is the energy associated with the second step. All right? The bond dissociation energy. Now we have been able to make sodium from being solid to gaseous phase in the first step. In the second step, we're able to change the molecular chlorine to a monatomic chlorine still in the gaseous phase. The next thing to do is to allow metal be metal. What metal is known for is that metal readily loses its valence electron and changes into an ion. And metal being itself loses its valence electron. Sodium being 281 has one electron in the valence shell. It loses that valence electron and becomes positively charged. And that is what happens in step 3. And there is equally an energy associated with the ionization of a metal. When metals lose their valence electron, there is energy content or enthalpy change that is required. And the enthalpy change that is required is called ionization energy, because that is what the energy that is associated when a gaseous metal ion loses its electron. Okay, so it is called what? Ionization energy. When gaseous atoms, mostly in the metallic form, loses their electrons in their valence shell to change into an ion, the energy involved is called ionization energy. Beautiful. So now we have sodium ion still in the gaseous phase. But again, you have the chlorine atom that was made in step 2 is still there. So we ultimately have to change it to a chloride ion. And it's simple, because this is a redox reaction. If sodium metal is losing electron, okay, that means that it's being oxidized. That means that chlorine atom is being reduced, which is the gaining of the electron. So what happens is that chlorine atom now gains that electron from the sodium metal, and ultimately in step 4 becomes chloride ion in the gaseous phase. So in step 4, you have chlorine being changed to chloride ion by accepting that electron. If that is clear, you can now agree with me that the energy involved in step 4 is called electron affinity, because this is the energy associated with the addition of electron to a gaseous atom. When gaseous atoms, which are usually non-metallic, accept electron to ionize, the energy involved in that process is called electron affinity, in which case here it is a negative value, which means that energy was released in this step 4, in this process, minus 349 kilojoule per mole, which means energy was released. Pay attention to the fact that here is plus 109, which is the enthalpy of sublimation. Pay attention that in a bond dissociation energy is 120 plus 120 kilojoule per mole. Both are positive values. Pay attention to the fact that the ionization energy is plus 495 kilojoule per mole, which is a positive value. So in step 1, step 2, step 3, energies were absorbed. But in step 4, because we have a negative value, energy is released. Enthalpy change could be about absorption of energy or release of energy. I believe it's clear. Beautiful. Now that we have free gaseous ions, it's simple. When you have negative charges, they attract. So the attraction the collision, because of course these particles are in gaseous state and they are ion, they are free moving, they are very unstable, they are eager to combine to make a stable compound, ionic compound or salt compound, sodium chloride. All right, that energy required, okay, or that energy released when 1 mole of an ionic compound, sodium chloride in this case, is made from the combination of their free gaseous ions, is known as the lattice energy, delta H lattice. The lattice energy, or you call it the crystal lattice energy, which in this case we don't know. That's why you put question mark here. Don't know what the energy is in kilojoule per mole. And lattice energy is denoted as capital U. And this is what we are supposed to calculate, having studied this BORN-HABER cycle. If that is clear, it is important we note at this point that lattice energies, capital U, are usually large negative values. So whatever is going to be here is going to be a very large value and has to have negative value, showing that that is an exothermic process, that energy was released ultimately in the process. This is beautiful. So to calculate the lattice energy of sodium chloride using the BORN-HABER cycle, this mathematical model, we must recognize that at the end of the day, the summation of all the enthalpy changes involved in the 5 reaction steps, okay, should equal what we call the overall energy change, or the standard heat of formation, which we measured using the calorimeter. Okay, so the energies involved in all these 5 steps should equal to the energy, should it be in this reaction, happen between the constituent elements in their standard form in one-step process to form sodium chloride. So the overall reaction is, again, is sodium in the solid state, half mole of chlorine gas, and of course you have sodium chloride, and this sodium chloride again is in the solid state. I believe it's clear. So again, you call it standard heat of formation or enthalpy of formation, or you call it what? Enthalpy of the reaction, okay? Which is measured using a calorimeter to be negative 41 kilojoule per mole. Now, according to Hess law, the standard heat of formation, which is this value, should be equal to when you add the summation sigma delta Hn. N represents the different reaction steps. So it means that the standard heat of formation should equal the summation of all the enthalpy changes for the 5 reaction steps in this reaction. All right? That is what Hess law tells us. But because we are dealing with an ionic compound, once we begin to apply Hess law in an ionic compound to calculate the lattice energy, we are using what we call the BORN-HABER cycle. The BORN-HABER cycle. So from the BORN-HABER cycle, the overall energy change in the 5 steps is, from this Hess law now, you understand that if this is true for Hess law and we're applying it to an ionic compound, you can now understand with me that delta H F naught, which is equal to the standard heat of formation, should be the summation of the 5 reaction steps. Okay, so we start with the first reaction step, which is what? The enthalpy of sublimation. That is the first reaction step. You add it to the second reaction step involving the enthalpy, okay, or what we call the bond dissociation energy. You add it to the third step. You have the ionization energy, which is the enthalpy here. Enthalpy change is the ionization energy. You add it to the fourth step. You have your what? Electron affinity, which is the enthalpy change in that. Then you ultimately add it to the last one, which is the what? Lattice energy. And interestingly, what we are trying to find is lattice energy. So at this point, the first thing we want to do is to, how do we make U the subject of the formula? Because that is what we want to solve. How do you make U the subject formula? So that is the first thing. So making the lattice energy, making U the subject of formula, the subject of the formula. You now rewrite all of this. I will try to be as explicit as possible so that every student or every learner will follow. I'll recopy everything here, which is this. plus this plus ionization enthalpy plus the electron affinity plus U. I'm going to put all of this in a bracket. Why I'm doing that is to show you that U is on its own and we have to make U the subject formula. So I'm putting all of this in a bracket. So the next thing we are going to do is that these whole enthalpy changes should cross should cross the sign of equality so that it can leave U alone. If that happens, you now believe me that you have this standard heat of formation. If this crosses sign of equality, it becomes minus bracket all of this enthalpy of dissociation, and you have your enthalpy involving ionization energy, and you have this, your electron affinity is here, which now equals U. That's where we have made U the subject formula. Just to be on the safe side again, we can decide to switch this equation so that everybody will be on the same page. You now have that U is equal to this minus everything in the bracket okay, ionization energy, and finally the electron affinity. That's where we've made the lattice energy U the subject of the formula. Now, next thing we are going to do is to substitute for energy values, okay? Substitute for energy values in the equation. We are going to put the values of all the enthalpy changes in the equation. And how do you do that? Since we are looking for this, we already know the energy value here, and it's giving us minus 411 kilojoule per mole. So the standard heat of formation is negative 411 kJ per mole. We know that. Minus. So everything, we are going to add up all these energy values, all right, and leave it in brackets. And how do we do that? We start substituting. For enthalpy of sublimation, the value is plus 109. So we are dealing with 109 plus, for bond dissociation energy, we are dealing with 120. 120 plus ionization energy is 495 plus electron affinity is, I'm putting it in bracket, minus 349 in bracket, then the general bracket. All these values are in kilojoule per mole. All right? So when you do that, you're going to have that your lattice energy is minus 411 kJ mole minus, when you add all of this together, okay, you are going to have 375. Of course, you have kilojoule per mole. All right? When you have minus, it's addition. The only thing is that your result will be what? Negative. So if we add the two values, 411 plus 375, we have 6, we have 8, and we have what? 7. Of course, it's minus, so what is going to be here is minus. So this is our value. That means that U is equal to minus 786 kilojoule, okay, per mole. Okay, kilojoule per mole. So this is how to calculate the lattice energy. Okay, this is how to calculate the lattice energy of a given ionic compound using the BORN-HABER cycle. I believe it made sense to you. If it made sense to you, kindly give me your like, your love, and share this video so that it can get to all the students who are looking for a way to appreciate some of the things we are dishing out to you on this particular page. And again, it is time you subscribe to my YouTube channel. The YouTube channel is now on, and I'm now uploading all our lecture videos on YouTube. You can check up our YouTube channel on Chem Class with Dr. Luther. So it's the same name on Facebook, Chem Class with Dr. Luther, and it's the same name on YouTube with Chem Class with Dr. Luther. Kindly subscribe to my YouTube channel and get other learners to subscribe as well. Thank you for being here. Until the next time, I remember your humble friend, Dr. Luther Nokwesili. Stay safe, stay away from trouble, okay? Bye.